Howdy. I wanted to take a look at problem number 23 from your textbook, in which Arlene is to walk across a high wire strung horizontally between two buildings 10 meters apart. The sag in the rope when she is at the midpoint is 10 degrees, as shown in the figure. If her mass is 50 kilograms, what is the tension in the rope at this point? This is a good example of a problem that occurs in two dimensions because we have forces that are operating both in the x and the y direction. Our approach to this problem is going to be exactly like our approach to all of the other problems in this chapter. Namely, we are going to create a free body diagram, follow that up with net force, and apply Newton 1 or Newton 2. So let's begin with a free body diagram for Arlene. Arlene is standing on the rope. Here's Arlene. She has a mass of 50 kilograms. And so the forces acting on her are going to be the force of gravity, which is a 500 Newton force, the weight acting on her. And also the rope will be pushing on her. Now, in what manner does the rope push? Well, remember that the tension always operates in the direction of the rope. And in this particular case, where she's standing, the rope to her right is going to be pulling to the right, and the rope to her left is going to be pulling to the left. So she really has the benefit of two different tensions that are combining to hold her up. And that's it for forces. The free body diagram is as you see. Now, what do we do about these forces right here? Here is the key learning point from this problem, and that is that the tension that is going off right here is at a 10-degree angle with respect to the horizontal, because this angle right here is also a 10-degree angle, and these two lines right here are parallel, and they're cut by the rope as a transversal. So this angle is a 10-degree angle, and likewise, same reason, this is a 10-degree angle as well, so that we have here 10 degrees. Now this free body diagram needs to be expanded a little bit, so let me pull it down a little bit larger. We're going to have a 50 kilogram Arlene, 500 newtons of weight going down. We're going to have a tension at a 10-degree angle like this, tension at a 10-degree angle like this. What we're going to do with our forces is the same thing that we did with our initial velocities for projectiles. We're going to take our forces and we're going to represent them with horizontal and vertical components. When we do, we're going to scratch out the original tension right here so that the original tension is now represented by a horizontal and a vertical force that add together to give the original tension. Same thing here. We've got Tx and Ty like so. And the virtue of doing this is that we can now express these components in terms of sine and cosine. The given angle on this side, 10 degrees, and Tx is adjacent to it, so Tx will be T cosine 10. And Ty is opposite 10 degrees, so Ty will be T times the sine of 10 degrees. And the same logic applies over here. Remember that when I'm showing values of forces, I'm only showing the magnitudes. So don't worry about the fact that this time that Tx on the right side is pointing this way, and Tx on the left side is pointing to the left. We'll take care of that in the equation. The arrows tell us which direction each Tx is pointing. Now that we have all of our forces represented with horizontal and vertical components, we can go through and add them up in the x and the y directions separately. First of all, for the sum of forces in the x direction, we have just Tx here and Tx right here. Those are the only two horizontal arrows. The Tx on the right is pointing to the right, so it is positive. And the Tx on the left is pointing to the left, so it is negative. And these two add up automatically to 0. Notice that no matter what value t is, t cosine 10 minus t cosine 10 will be 0. And physically that means something. That means that these two ropes are going to balance each other. Their tensions will cancel out in the x direction. Now if we look at the force in the y direction, the sum of forces in the y direction are going to include Ty on the left, which is pulling up, so that's positive. And Ty on the right is pulling up also, so that is another T sine 10 degrees. So we really have 2 T sine 10 degrees. And then her weight of 500 newtons is pulling down, so we have a downward force. And that is equal to 0 because our leaning is not accelerating. So this gives us now two equations. The first equation is a trivial equation. It just says 0 equals 0, and we don't get any useful information from it. But the second equation is very useful to us. You can add 500 newtons to both sides. You can divide both sides by 2 and by the sine of 10 degrees. And the sine of 10 degrees is just a number, but I wanted to represent my tension like this for just a minute before I punch the values in. When we do punch the values in, sine of 10 degrees turns out to be a pretty small number, so that 500 divided by 2 sine 10, if you try it in the calculator, should give you 1,440 newtons. That's a pretty large tension. That's the equivalent of the weight of about a 300-pound man. And the question is, why is there so much tension? And the answer is that this angle of 10 degrees is a really small angle, so that when I divide by the sine of 10 degrees, I end up with a very large tension. In other words, the flatter the angle that Arlene is making in the rope, the more tension there will be in that rope. The implication is that it would actually be impossible for Arlene to stand on the rope and not have it go down at all. 0 degrees would give me a 0 in the denominator, which would correspond to an infinite amount of tension. It would take an infinite amount of tension to keep the rope from sagging at all. So again, the key learning point in this problem is that when we have forces that go off at strange angles, like this one did, then we can resolve those in x and y components so that we can then add up forces in the x and the y directions separately. I hope this was helpful.